Okay, let's move on to the final chapter, which is chapter 9 on correlation and regression. Okay, correlation is the relationship between two variables. This is a very powerful tool in mathematics. This regression concept allows us to do a lot of prediction based on data. We're just going to focus on linear, but there's all sorts of regressions you can do. So we're going to examine a scatter plot, ordered pairs x and y, and we're going to look at the shape and see if there is some kind of linear relationship. So here's some examples. This first example, we can see the data follows this line pattern, and the data is decreasing. So we call this negative linear correlation. Here, the data points increase. This is positive linear correlation. This one in the lower left, well, there doesn't appear to be any correlation at all. There's no pattern in the data. Now, this last one, there clearly is some kind of pattern going on. And it's possible to do a quadratic regression here and model the data. But for this course, we're only going to focus on linear. So let's look at this example. We're talking about GDP of a nation and the CO2 emissions. And we want to see if there's some kind of linear relationship between these two things. If we plot the data points, there appears to be some kind of linear relationship. It appears to be increasing. Now, it's not perfect. To be honest, to determine if this is truly linear, we'd probably get some more data points to make sure that it does form a straight line. So we call this positive linear correlation. Here's another example. So we're looking at hours of exercise and GPA. So we're interested if there's a connection between the number of hours someone exercises and how well they perform in school. So this is a good place to start if you're doing a study like this, is you'll see if there appears to be some kind of relationship. If we plot the data points, well, if there's a relationship, it's a flat line. There doesn't really appear to be any pattern. If we wanted to flesh this out, we would survey some more people and collect some more data points to see if there is a pattern. So there appears to be no linear relationship here. Now here we're looking at a science study. We're looking at the duration of eruptions of a geyser and then the time between eruptions. So what you do is you go up to this geyser and you have a stopwatch. You measure how long the geyser goes off, and then you measure how long until it goes off again. If we plot this data, there does appear to be a positive linear relationship. Now, we can mathematically measure how good the data fits the linear pattern, and this is called the correlation coefficient. And this is a number that tells you essentially how good the data fits the model. Now we have this long, complicated equation here, and this is nothing you need to worry about. We're going to be doing all of these computations in the calculator. We're going to put the data in the calculator and make it compute the R value. The population correlation coefficient is represented by this Greek letter rho. So just like in the past where we've had sample and population statistics, here the sample is R, the population is rho. Now the correlation coefficient ranges between -1 and 1. So remember, if it's 0, there's no relationship whatsoever. Now, if it's very small, let's say zero point 0.1 or negative zero point 0.1, that's not a very strong relationship. But if it's much higher, let's say it's 0.98, we'll think of that as 98%. That's pretty high, so that's pretty good. Now, it can also be negative, and that just simply means the line is going down. So if you have negative zero point 0.5 over here somewhere, 0.95, that's still a strong correlation. So if it's -1, that's a perfect decreasing line. 0 is no correlation. 1 is a perfect positive correlation. So here are some examples of various types of correlation. Here, perfect straight line, R is 1. This next one, there is a linear relationship, but it's not as strong, so that's 0.81. This one, there's not much in common at all. It's 0.45. That's pretty low. Perfect negative correlation. This next one, there appears to be some linear correlation negative, and it's pretty strong. It's pretty close to a straight line. This last one is all over the place. There is no correlation at all. Now, we can skip all of these steps. We will not be using this formula to get the correlation coefficient. We're going to do this on the calculator. And let's look at that right now. What we're going to do is take this GDP CO2 emissions data, and we're going to put it in the calculator and find out what the R value is. So if we go to the calculator, we're going to input the data in the lists, just like we have in the past. Go to Stat, Edit, and we're on the lists. We're going to put our data in L1 and L2. Clear out any data that's already there. I'm going to put GDP in L1, CO2 in L2. Then I'll go to the next column, and we'll put in CO2. Now, remember, this is for paired data. We need to make sure every item is paired up. If you have any extra data, it's not going to run the regression correctly. Once the data is in, simply clear out, quit. Again, we go to Stat, Calculate. We want linear regression, which is option 4 right here. Now, some of you are going to see different things on your calculator menu here. What you want to do is hit linear regression. We need to tell it which lists to use for data. So we need to say L1 and L2. Second, L1, use the comma key. Second, L2. Now, what you see here, this is what we need. R equals 0.874. Now, this is important. We're going to use this again in just a minute. But for right now, if we look at this R value, 0.874, that's pretty strong. You can call that, around 87%, which is semi-strong positive correlation. Now, this R value can also be negative, and that's okay. It just means the line is decreasing. And there is the R value. We can do the same thing on this Old Faithful data. If we put it in, we get an R value of 0.978, which is very strong, which means there is definitely a relationship between this data. Okay, so what we're going to do is use critical values of R. Using the calculator, we can get the R value. We need to determine if that's good enough to say there is significant correlation in rho, the population correlation coefficient. So what we'll do is use this table. Let's look at the table for just a moment. So critical values for the Pearson correlation coefficient. You'll have two cases. Either alpha is 0.01 or 0.05. N is the sample size. Now, N is the number of pairs of data, not the number of data points that you have. So it's how many ordered pairs you have. So we go down and match the correlation coefficient. So this is the cutoff of whether it is significant, yes or no. If it's greater than this critical value, yes, it's significant. If it's less than, no, it is not good enough. So if we look at the CO2 data, we just found the R for that. Let's go to the table. They want us to test it at the 0.01 level. If we go back to our table, go to the 0.01 column, the N was 5 pairs of data, so that's 0.959. Okay, that's not correct. 0.959, there we go. Now, this critical value is very high. We're not going to draw a curve like we did with hypothesis testing, but we can draw a straight line. This is 0, this is 1. The critical value is 0.959. The R value that we computed from the calculator is 0.874, which is going to fall below somewhere. Because it falls below, there is not enough evidence to conclude that this is significant. So if it landed over here, yes, that would be significant, but because it's below, no. There may still be some linear relationship, but it's not good enough at the 0.01 level. So let's look at this again with the Old Faithful data. So there are 25 pairs of data. Alpha equals 0.05. Okay, so here's what we're going to do on this problem. We're going to use this information to find the critical R value. They've already given it to us in this case. So instead of putting it in the calculator, we're going to use R equals 0.979. So again, let's draw a picture. Here's 0, here's 1. We need to find the critical value that is the cutoff. there are 25 pairs of data. The alpha value is 0.05. If we go to the table, 0.05, go down to 25, 0.396, which should be over here somewhere. 0.396. If it's smaller than that, no, it's not significant correlation. If it's greater than that, yes, there is. Now, the R value that we have, 0.979, is pretty high. That's pretty close here to 1, which is greater than the critical value, which means, yes, there is significant linear correlation here. Okay, now, we can use this critical number method, but we can also use a hypothesis test. Now, don't be scared. This is actually pretty easy in the way of hypothesis testing. So here, we have 3 types of problems: left-tailed, right-tailed, and two-tailed. Now, instead of talking about mean and proportion and standard deviation, we're talking about rho. And rho is population coefficient. So let's translate this. If rho is greater than or equal to 0, there is no significant negative correlation, which makes sense because if it's greater than 0, it would be positive. If it's less than 0, there's significant negative correlation. If rho is less than or equal to 0, there is no significant positive correlation. The alternative is greater than 0, significant positive correlation. Now for two-tailed, we don't know whether it's positive or negative. So we say rho equals 0 means no significant correlation. Rho is not equal to 0 means there is significant correlation of some kind, and that could be positive or negative. So we'll use the t-test. We'll use this formula in order to find the t-value. Now the only 2 variables in here are n and r. N will be given to you in the problem. R is the correlation coefficient that will come from the calculator. Now we have to be very careful here. In the past, whenever we've done the t-distribution, degrees of freedom have always been n-1. Because we're talking about 2 variables, we're talking about paired data, degrees of freedom is not n-1, it is n-2. So make sure you put this in your notes. Students tend to do n-1 because we've used it for so long. So, state the null and alternative hypotheses. Specify the level of significance that will be given to you in the problem. Degrees of freedom are n-2. Determine the critical values and the rejection region using the t-distribution. Find the standardized test statistic. Make a decision to reject or fail to reject. Interpret this in terms of the claim. So in a previous example, we had 10 pairs of data. The R value is 0.874. Test the significance if the alpha value is 0.05. Okay. So the question says, test the significance of the correlation coefficient. Now, they don't say anything about positive or negative. They're just saying, is there correlation of some kind? Which means the null hypothesis will be rho equals 0, which means no correlation. The alternative is rho is not equal to 0, which means, yes, there is correlation of some kind. So let's draw a picture for this. It's our good friend, the t-distribution. Because the alternative is not equal to, it's a two-tailed test. The alpha value is 0.05. Remember, because it's two-tailed, we have to split that two ways, which means there's 0.025 over here and 0.025 over here. Let's find t critical. Using our tables. Go to the t-distribution. Two tails, alpha is 0.05, we go to the center column. N equals 10. Degrees of freedom are 10 minus 2, which is 8. So if we go down to 8, 2.306. Now, because it's symmetric, the other one will be negative 2.306. Let's find the test statistic using the formula. Now, we have R. That's 0.874. Plug that into the formula. And simplify. .08. Now, this is the test statistic. On our picture, we know the regions for reject and fail to reject. H0. Our test statistic was 5.08. That's going to be over here somewhere. Which means we reject the null hypothesis. So, what does that mean? The null hypothesis, we reject that. It's out, which leaves us with the alternative. Rho is not equal to 0. Now, don't think of that not equal as a bad thing. If rho is not equal to 0, it means there is significant linear correlation of some kind. And that's what they're saying here in the text. And really, I wish they had drawn a better picture of this. Compute the test statistic. Compare it in the diagram. We have our critical values. This t is way over here at 5, so it's definitely in the rejection region. You reject the null hypothesis. There is enough evidence to conclude there is significant linear correlation between GDP and carbon dioxide. Okay, this last section on lurking variables is not something you need to worry about. And that's it, we're finished.